as you can see, we're going to go with the good old Sharpie and paper. Let's see how this goes. So let's get right into function notation. So today's video, we're going to be looking at something like this. When we have something like this, we can look at it and say, or we can represent a function in terms of f of x, where f of x is going to be used to represent the value of the dependent variable, which is f, for any given independent variable, which is x. So it might look something like f of x equals x squared. Usually we're used to seeing something like y equals x squared, but now we're going to represent the function f of x. So whatever x is, we can plug into here and represent it like that. So it might make more sense if I just get into an example. So let's say we want to write a function for temperature, and let's say we have a problem where we have a temperature that is for some, say, system or some component or whatever, like we were talking about. Say it's at 11 degrees Celsius, and every day that passes by, we add 0.015 degrees Celsius. So let's say we want to represent this in a function t. So let's write that out. Let's write t of, and let's pretend like day is a letter D. So t is our independent variable that can change. It doesn't depend on anything. But t, the value of t does depend on d. That's why this is the dependent variable and that's the independent variable. So we're going to write t of d is equal to 11 plus 0.015 d. And now we say, like, where t represents the temperature in degrees Celsius and d represents the number of days that has passed by. So, and in this, or let's try something, or let's just change this slightly. Instead of saying, let's make it easier, 5d. That way we can easily map this out, or like write it out. We can say that, okay, if this is the function for temperature, let's say temperature T, and let's say on day 0, let's put that in. T of 0 is equal to 10 plus 5 times 0. 5 times 0 is 0, so it's just 10. So now let's do 1. Let's do, and now we have 10 plus 1 times 5 is 5 plus 10 is 15. And we can keep doing this. We can put a 5 here. T of 5 is equal to 10 plus 5 times 5 is 25 plus 10 is, and we can even map that out. Where D is here, we rough sketch, but that is our line. So function notation is just a different way to represent the function. And that's what we see here. So let's try one more example. I'm just going to put this here, and here I'm going to basically just write two functions. F of x is equal to x squared minus 3x. And I'm going to write g of x is equal to 1 minus, I don't need this, sorry. So now let's push into a problem. Let's do this. Show f of 2 is greater than g of 2. Let's prove this. And that is as simple as saying, okay, f of 2 is basically 2 squared minus 3 times 2. That's all it is. I put in the 2 where the x is, and now I can solve this. Negative 2. Now we can do g of 2, which is 1 minus, well, yeah, 2 times 2 equals 2 times 2 is 4. So now we know that f of 2 is negative 2 and g of 2 is negative 3, and negative 2 is greater than that. So that's how we show that g of 2. These 3 dots is my way of saying therefore. That's how I got into the habit. Let's say we want to do something even more weird. Say we have something that says, show me what this would look like. G of 3b. B is now a new variable that I want to sub into x into this formula. That's very simple now. I just do 1 minus 2 times 3b, which is equal to 1 minus, and if I expand that, negative 2 times 3 is negative 6, and negative 6b. That is g of 3b. I can also do something a little more complex, which is let's see, something a little more complicated. Now, let's say I want to find out this. This is very, don't let it confuse you. Let's do this one at a time. Let's do for f of x first. Let's do x squared minus 3x. And let's plug in c plus 2 squared minus 3 times c plus 2. Right? And then on this side we have 1 minus 2x, which becomes 1 minus 2 times c plus 2, which becomes 1 minus plus 2 squared. So then we have this negative 3 times c, which is negative 3c minus 6. So if we're looking for this, we have f of c plus 2, which is this entire thing. Well, wait, let's simplify this. Let's c squared. We have 2c's, so 4c minus 3c is plus c plus 4 minus 6. That should give me negative 2. So that's what we have. And that one too. 1 minus 4. I can do negative 3 minus 2c. So now I have this is that and that is this. But to find this entire expression, I need to subtract this from this. So let's write that out. C squared plus c minus 2 minus. And because I'm subtracting these terms here, if I was to open this bracket, it's kind of like I have a negative 1 in front of it, so I'm going to multiply that negative 1 into each of them, and that'll give me negative, negative, a positive, negative, negative, positive. So that'll give me plus 3 plus 2c, and I have c squared plus c minus 2. Now I just need to add, collect the like terms, so I only have 1c squared, and then I have a plus c and another positive 2c, which will give me 3c plus 1. So this entire expression is equal to these functions are defined here, and that is how we solve using this function notation. So yeah, I hope this was a good intro to our grade 11 math series. Hopefully this made some sense, and yeah, that's it for this video, and I'll see you in the next one. Okay, welcome to another video on math. Today we're going to be looking at parent functions. So parent functions are basically, let's just write out a few. That would be considered a parent function because from this we can make a whole bunch of functions. We can do mx plus b, like any kind of format with a slope and a y-intercept. We can do 10x plus 1. We can do 1. We can do x plus 3 or 2. This is what's considered a parent function, and from that we can create all kinds of child functions. Another one we can do is like our quadratic one. So we can have f of x equals x squared, or we can do 2x squared or x squared plus 5 or x minus 5 squared, or all of them 2x squared, 2x minus 5 squared plus 5. And so yeah, all these functions are children of this parent function. So today we're going to look at the main parent functions that you're going to see quite often in the upcoming many videos. There's also, this is called the square root function. Well, let's just write this linear. Let's write this one. The square root function. And then we have, let's do the reciprocal function. And then we also have this is the absolute function. Well, this is the absolute function. So let's look at these functions one at a time. So basically, let's do the linear one first. And this is very easy to understand once we map it out. Like, say we put in 0 for x, this is 0. We put in 1, that's 1, 2, 2, dot, 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 100, 100, right? So, this graph, that's not straight at all, will basically be this. And obviously, well, this is the parent function. If you were to modify it like x plus 1, it would be here. And we know that from our previous year's lessons. That is our linear. And let's do the quadratic one. F of x equals x squared. So at 0, we have 0. 0 squared is 0. 1 is 1. 2 is 4. Remember, this is x. This is f of x. 3, 9, 4, 16. So we know that this is going to go like this: 0, 0, 1, 1, 2, 4. But also, if you were to plug in -1, you still get 1, because -1 squared is also 1. Same with -2, -3, -4. You also get the same values. So at x, at these negative values, you also get the same. I'm trying to be creative, artistic here, or not so creative. So yeah, and this is my quadratic. Let's do the next one. F of x is equal to root x. And when we do this, we will get, let's just start plugging some numbers. Square root of 0 is 0, square root of 1 is 1. I can do 2 as well, but it's going to be a very weird decimal number, so I'll just skip to 4. 4 square root is 2. Let's do 9. Square root is 3. So if you were to graph this out, 0, 0, 1, 1, at 2, 3, 4, you'd get 2. this as it curves up a bit and goes to the right. That is our square root function. Pretty straightforward. Next we're going to do the reciprocal function, which is so here, if you put say, I'm trying to explain this in the best way I can. Say if you put 0, actually you can never put 0 here, sorry. You can't have 0 as a denominator, so this function will never touch 0. It'll get close to it, but it'll never touch it. So let's do 1. 1 over 1 is 1. And as this number gets bigger, let's say at 2, this is going to become 1 over 2, so 0.5. If it becomes 4, it becomes 0.25. Right? So it'll keep getting smaller. So that's going to go like this and get very close to the x-axis but never touch it. And actually, if this gets smaller, if x gets smaller, instead of saying 1, 2, 4, if I put 0.5, 1 over 0.5 is 2. So that'll be 2. This is 0.5 here, and that's 2. And the smaller this number gets, the bigger this number gets, so that's going to go up that way. And that is a reciprocal function in the positive side. However, if I was to plug in negative numbers here instead, say I put this negative number here, I'd get a negative. That'd be here. Same with this. Negative 2 would be negative 0.5. Same with that. That should not be touching, but just pretend it doesn't. So this is what our reciprocal function looks like. It gets really close to it but never touches it. And the only one left is the, I guess the absolute one. I can draw that here. That is the same as our linear function. F of x equals x, except instead of that, the absolute value of something just means that if it is a negative number, so say negative 1, the absolute value of negative 1 is just 1, the positive version. So while in here, if you had a negative 1 input, you would have a negative 1 f of x that's here. But in this function, we don't. If we put 1, 2, 3, you get 1, 2, 3. But if you put negative 1, negative 2, negative 3, you still get 1, 2, 3. So at the negative x values, negative 1, 2, and 3, you're still getting positive y values, or sorry, f of x values. And this is our absolute function. So yeah, there you have it. Our five parent functions. Let's just recap here. This f of x is going to be a linear function. Our square root function, that's the quadratic. Our quadratic parent function. Our reciprocal function, the 1 over these are very rough sketches. Our absolute and then our square root function. And there you have it. Our 5 parent functions that we're going to be abusing in the next several chapters. So these are the basics, and then we're going to start manipulating them, and I sound like a very toxic teacher right now, but don't worry, this is all going to be very easy once we understand these functions and how they look, and then once we apply changes to them, they're going to be very simple. So that is all for this video on parent functions. And yeah, I shall see you in the next one. Okay, so today we're going to be doing domain and range. So domain basically refers to all the values in the x direction, and range is all our y values. So when asked to state the domain and range of a specific relation or function, they basically want you to define or explain or say that, listen, this is what all the x values are allowed to be, and this is what all the y values are allowed to be. So let's look into one. Let's have an example. It's not perfect. Let's do and say we have at 1 we have 2, and then at 2 we have 3, and then at 3 we have 4, and so on. So let's say we have these points, right? And these points are, if we were to map them out as x and y coordinates, at -3 we have a value of -2. At -1 we have 0. At 0 we have 1. At 1 we have 2. At 2 we have 3. And at 3 we have 4. So now we're going to basically write the rules for domain and range. Let's start with domain. The domain for this is basically what are our x values allowed to be in this particular set. This is a limited set, so we only have these 7 points. So we can write our domain is equal to literally these points. And same with our range. So we can write -2, -1, 0, 1, 2, 3, 4. Or there's another way to write this. We can write x is equal to all the integers between -3 and 3. So this then, well, this basically means this. X is all the integers in this range, domain, but like within these two numbers. We know that from -3 to 3, it's every integer. And same with the y. And I put this sign here. This means A is less or equal to B, or B is greater or equal to A. That's what this sign means right here. And the opposite is exactly what you think it is. Well, yeah. Basically whatever's on the opening side. That's what this means. So yeah, because we do have values of 3 and -3, so we do use the equal. If we were to use, instead of this, we were to use just this, it means B is strictly greater than A, and they cannot be equal. So, yeah. So in that case, you could write this as -4. So the integers greater than -4 and the integers less than +4. So yeah, that's one example. Let's do another one. Let's do one where we have, let's say we have -5 and we have a +5 and a +10. Let's say we have a line, let's say that's 5. Let's make another line here that goes from -5. I'm gonna draw an open circle and let it go till there. Oh no. Ignore that part. Oh, let me draw that again bigger. Let's draw this, and it goes to here, and that's a closed dot. And then let's do somewhere here, let's make another one, an open dot, and go till just past 10. Okay, now that we have this, let's look at the domain and range for this function. So one thing that I want to point out is that when you have an open point like this, it means this point is not included, but a closed point is let's say this line happens at 2 and this line happens at 6 on the x. So right away we know the range, our range, our y values for this particular function can only be 2 or 6. There's nowhere else that y value is going. But for our domain, we have from -5 to 5. That's one domain, right? But remember, the open one is not included, so it's not. So from -5 to 5, this 5 is included, but this 5 is not. So if you were to write that, we could write is because you'll notice I didn't put the equal sign here because this -5 is not included. But this 5 is, even if this one is open, this one is included. But let's say this ends at 11. So actually the range will continue all the way to 11. And that is the domain and range for this particular function. Let's do one more, or even maybe two, but let's see. So let's say we have let's say at 3, 1, we have a parabola that opens up. Sorry, it is 1, 3, x and y. So now the domain and range for this. Let's look at the range first, or let's look at the domain. The domain, as we can see, as this continues, this will go on forever in that direction, and this will go on forever in that direction. So our domain is XER, and that basically means all, like any real number, x is equal to all real numbers. And then for our range, we just have to look at x is all real numbers, and the only restrictions we have, because from here and downwards we have all our y values, but from 3 and upwards we don't. So oh no, I don't know why I put x. It should be so the only condition we have here is that our y value can only be less than 3, and that is the domain and range for a parabola. And if you wanted, we could even do, let's say we had a circle with a radius of 5, and its center was at the origin 0. know that our x and y values will go all the way from, like say, let's do our x first. Our x can be all the numbers from -5 to 5. We have a value for every x. Same with y. So for a circle, it's very easy. Our domain is XER. Let's do -5. -5 to 5, and same with our y. And that has been domain and range. For functions, you might be asked in the future to write the domain and range for a function after solving it or something. But basically just look at all the x and the y values, what they can and cannot be. One thing you'll notice is that I went from XEI to XER. When I say I, that means integer. So I use that for this one here. These are integers because I have plot points. I don't have anything in between. So I don't have a -2.5 for x or a 0.5 or 1.5. I do have integers. Integers are strictly 1, 2, 3, -1, -2 are whole numbers. But when I use XER, this is x is equal to all real numbers. So real number is any number. It could be to any number of decimal points. It could be here, 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 here. Like, yeah. Well, I just noticed I could write this as I. But yeah. Sorry about that one. This one. Our range. Yeah, our range is YE. That should be R. Sorry. That should be R. This could be YEI. Well, that's not necessary. We only have 2 points there. But yeah, I hope this made some sense. And I shall see you in the next one. Okay, so in this video we're going to be looking at the inverse function. So basically the inverse function, it sounds a lot more complicated than it actually is. But an inverse function actually is the reverse of a original function, which is exactly what it is supposed to be. So let's look at an example. So let's say we have a function f of x is a function of x, and the function is 2 minus 5x. This is the original function, and this is a linear function. So in order to inverse this, like what this does to x, like what this f of x value depends on is what happens to x. So x is being multiplied by 5 or -5, and then it's being added to 2. So it's actually positive 2 minus 5 times x. That gives us our f of x value. So to inverse this function, we need to do the exact opposite. And the easiest way to do this is to swap x and y values. Or, sorry, variables. So let's say we have this example. And what I'm going to do first is put a y here instead of f of x. And then I'm going to swap it. After swapping it, now I'm going to solve for y. Basically, I'm going to get y alone. This is just some simple algebra. And that will give me my inverse function. So, one of the first things I'm going to do is I'm adding 2 to this side, so I'm going to subtract 2 from both sides. And that'll give me x minus 2 equals negative 5y. So I have negative 5 being multiplied on this side, so I'll divide both sides by that. So now I'm left with y is equal to this, which if you apply the negative, it should be 2 minus x over 5. And this is your inverse function. So if f of x is equal to 2 minus 5x, our inverse, and this is how we notate inverse, is 2 minus x over 5. And yeah, the inverse is also a function. So that's how we do that. So let's look at another example. Let's look at a plot. Let's say we had one, two, three, four. That's negative 4. Let's say we had 1, 2, 3, 4. That's positive 4. Let's say we had 1, 2, 3, 4. 1, 2, 3, 4. So let's plot some points. Let's say we have a point here, here, here. Let's put a point up here. Let's put a point down here. And then let's put a point right here, negative 4, negative 1. So now let's say I have these points and I ask you to graph the inverse function of this. And this is actually very straightforward. It might confuse you, but what you can do is let's draw an imaginary line. Let's say it's going and this imaginary line is basically y equals x. So now that we have this imaginary line, now I'm going to plot a mirror of everything, basically. So remember when I said we're going to swap the x and y coordinates, so you'll notice that let me just put a notation that what I'm going to do in orange is our inverse. So right off the bat, if we have a, let me just use both. If we had this point, -3 comma 1, this will become -3, and same with all of them. So this will become right here, and that is basically a mirror of that. Same with this one. -2 comma 1 will become 1 comma -2. Same with this one. 1 comma -1 will become, -1 comma 1 will become 1 comma -1. You can see that it's a direct inverse. This one, we can just eyeball it and we know it goes here. And that's that. Like, let's look at this one. 4 comma -1. That becomes -1 comma 4. That's -1 comma 4. That's all the way up here. Same with, what else am I missing? Oh, this one. I have 0 comma 3. That becomes 3 comma 0. And our 1, 2, 3, 4, 5, 6 points have been plotted. 1, 2, 3, 4, 5, 6. And it's as simple as that. So let's do one more. And this one is going to actually be a function, a linear graph. Can't use that side. Let's do a proper function. Okay. Those are just intercept points. I'm gonna try to draw a line here. And this is going to be y equals g of x. So you might be wondering, maybe I could find the slope and the intercepts and create the full function, the y equals mx plus b function, swap them, and then write it out again, x minus b over m equals y. You could get the inverse function like that and then plot it out. Or, because that would, you would also have to like redo this or move this around to become into this format. But it's too much work. I know right now that we have the intercepts here for our our g of x function, we have 0, comma, let me just write it here. Our y-intercept is equal to 0, comma 4, and our x-intercept is equal to, I want to say that's, that should be 5. I'm a little bit off here, but it's okay. Let's put that as 6. Our x-intercept is 5, comma 0. So when we want to do the inverse, let's swap these around. Our y-intercept will become, we're going to swap the 2, and that'll give us that will give me, this point will be mapped to the inverse. So 0, comma, sorry, I don't know, I must be half asleep right now. I'm just confusing myself. This is a 3. So our new value will be mapped here at 3, comma 0. And that is confusing. So our y-intercept will go from, our y-intercept, which was 0, comma 3, will invert and become 3, comma 0. And that'll become our new x-intercept. And our x-intercept, which was 5, comma 0, will invert and become our y-intercept. Well, this is going to be 0, comma 5. 0, comma 5, that's up here. And that is my new line. So this is y equals g of inverted of x. Wow, I actually confused myself there. But happens to the best of us. Just gotta retrace your work backwards. And yeah, that is just taking it one step at a time, and yeah, that's all for the inverse function. I'll see you in the next video on to something maybe more confusing. Okay, so in this video we're going to be doing function transformations. So in our previous videos we learned about parent functions. So that is going to be something we're going to be looking at today. So let's jump right into 2 different functions. Let's do y equals and so we have these 2 functions, and basically we want to see how the difference in these 2 values, like both of these come from this function, are quadratic. The only difference is one has a positive 4, a positive integer in front of it, and the other one has a fraction. So let's look at how that happens. So let's do this. So let's let's say we have a regular quadratic. And now let's put in this one in green. So this black one is our x squared. Now our 4x squared is going to be slimmer. And that is because if you were to write out these, say, x and y values, you would have, when this is 0, this is 0, this is 1, this is 1, this is 2, this is 4, this is 3, this is 9. However, for this one, for y equals 4x squared, for the same x value at 0, it's 0, but at 1, when x is 1, we have 1 times 4, and 4 squared is 16. That's why at 1, instead of like where we may have had 1 here for the x squared, we have 16 all the way up here. That's why it becomes more narrow. And similarly, for this one, for x equals 0, we have 0. And let's do x equals 5. At 5 now, we have 5 times 1 over 5 is 1. 1 squared is 1. So now, at x equals 5, which is all the way here, we have a 1. So, by that logic, you have something like that. It's a much wider one. Is how we can see how these function transformations impact our function. And we'll do one more. Let's do our absolute graph. If you remember the absolute one. That is this is our absolute function, where, -1 is 1, -2 is 2. And now we're going to do the same thing as before, but now we're going to use these two functions. And we're going to see how this impacts our graph here. So let's do this one first, 0.25x. So if we were to write this out, x and y. Remember, x is being divided by 4. 0.25x, which is our y absolute value. So let's write -4, and that'll give me 0.25 times -4 will give me -1, but the absolute value of that will be that. And same with 0 will be 0, 4 will be 1. So before at -1, well, here we had -4 was 4, and 4 was at 4. So say these two are 4, and that's 4, -4, sorry. And now at the same x values, it's now at 1, somewhere here. So as you can see, that's a straight line. And now we see with a fraction here, or this could also be written as the absolute value of x over 4. We have a wider graph. Okay, well, that's all for this video. I shall see you in the next one. Okay, so in this video we're going to be transforming the root function, which, as we recall, is f of x equals root of x, right? So in here, the best way to go about this is to just simply try to graph something in the form of the root function. So today we're going to try to graph out this function here. So we know that this is our parent function. And we're going to do this one step at a time. So from previous videos we know that this -1 is our vertical translation. So that's and we know that we're going to have this number 2 is going to give us a horizontal compression. Or don't, let's do the other translation, the horizontal one. And this horizontal translation is going to go 4 units to the left. And then we're going to do our horizontal compression. Enough space. By a factor of you'll see why that's half in a second. And then we have a vertical stretch by a factor of 3, which is that. And then I almost missed that, it's the negative sign. So we're going to have a reflection on the x-axis. this this function, this parent function, that will get us from here to here. So let's start by writing this out, or sketching this out. So let's put this at 0, and let's do 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. So we know that our original function is going to look something like this. This one right here, f of x. Our coordinates at 0. X value, we're going to have 0. At 1, we're going to have 1. When we have an x value of, say, 4, then we're going to have 2, which is here. And so 1 to 1, 4 to 4, 4, 2. And then we also have another 9, 3. So when you plug in 9 as x, the square root we get is going to be 3. That's our y value. So that is going to look something like that. And then we're going to start doing our transformations to it. So let's do this 2 first, right here. This 2 is going to be a horizontal compression. So what happens when we start writing the 2 out? F of 2 of x. At 0, we still have 0. But now, our horizontal compression, so when we have, say, a half now, to get the same output as 1, in order for this to be 1, now we have to put, because now this is 2x, so this is basically this, y equals root 2x. So in order for this to be 1, this entire side has to be 1. And that's only true when you have 1 under here. So if x half times 2, that'll give me 1 under the square root. And that will give me 1 to 1. And that same goes for here. To get the same value 2, I can't put the same x here. I have to put 2x under the bracket. So 4 over 2 is 2. And then same with 9. So instead of 9, at 3, my x value will now be 4.5. So now, if I was to write the exact same coordinates here, now at half, I have 1. So half of, so before it was 1 to 1, it was there, so now it's about here, smaller, and then 2, 2, and then I have 4.5, and that's 3, which is somewhere there. And that's how my y equals 2x. And understandably, if I was to put a smaller number there, like instead of 2x, I put 1 over 2x, these numbers would have to be bigger, so it would actually be thinner down here. stretch right now, it's a horizontal compression. So now that we've done that, let's move on to the next transformation. Let's do our vertical factor of 3. So now we're going to have 3 times f of 2x. So now, whatever this was, now we're going to have to put in, we know 0 is going to be the same. But now we have a vertical stretch of 3, so whatever this was, we're going to multiply by 3 to obtain the values that we're looking for. So for at half now, our half was over here somewhere. Now instead of that value at 1 over 2 is going to have a vertical stretch of 3. So my y value is going to go from 1 to 3. And same for here. So 1 over 2, and now it's going to be at 3. And for my value at 2, what I had before was 2. Now it's going to be 6. And what I had before for 4.5, now it's going to be 9. That's about here. And that's y equals 3 root 2x. So now let's do another transformation. So far it's pretty straightforward. Let's do our reflection now. Let's do the reflection. So now our reflection is going to be on the x-axis. So now instead of 3f of 2x, we're going to do negative 3f of 2x. So now, whatever we had before for our x as the, now our output, basically, so let me write that one out too. So this one here is y equals 3 times 2x. So whatever the last one was is multiplied by 3. And now the output, our y value, is going to be the negative of that. So our y values here will become negative, except our origin. So same with our 1 over 2. That's going to be negative 3. Our 2 will become negative 6. Our 4.5 will become negative 9. So let me So now let's draw this one. So we're going to have this value flipped. So that will become from 3 to negative 3, and at 2 we're going to have, instead of 6, we're going to have negative 6. And then at 4.5 we're going to have negative 9, which is somewhere here. So now you can see So here, these two. So we're gonna go down 1 and left 4. So each one of these points will go down 1 and left 4. So we can actually write that out here. So this will now be -3. So we're going to have something like this. So our origin is now going down 1. So our y value is being decremented by 1. And then our x value is being shifted over left. So -4. And now I can just do that with all of these. So 0.5 minus 4 is -3.5. 2 minus 4 is -2. 4.5 minus 4 is 0.5. And same with these. I just subtract 1 more because I'm going down. So now I'm -4, -7, -10. Now these are now my new points. So -4, -1. Now I have that point. That's my origin. So this one went -4 and down 1. My next point is -3.5 and -4, which is somewhere here, which is that point. And then same with what do I have here? I have -2, -7, and then I have 0.5 at -10. And that is my f of x, the original one. So yeah, now we see how step by step we can move the graph. And one more thing we can do is just quickly state the domain and range. So our domain is how many x values we have. So x we know starts from -4 and we'll go that way. So x will be greater or equal to -4. Why not exceed r? And our range is going to be, I think the highest y value we have is -1, and then it only goes down. So our y is going to be all real numbers, but limited to y is greater or equal. Sorry. Y is less. No, I had it right the first time. Y is less or equal to -1. But yeah, x is going to continue in the positive. Y will only go down. Okay. So that's what I have, and I'm going to give myself full marks. So yeah, that's all for this video on transforming the root function. I hope I didn't confuse anybody, and I hope the colors helped. But yeah.